Welcome back, everyone. In this video, we're going to start Chapter 7, looking at molecular structure. And in this video, we're going to focus on the concepts of electronegativity and bond polarity. So, as I mentioned in an earlier video, when we have covalent bonds, those electrons are shared between the two elements that are involved. However, not all covalent bonds are the same. And depending on which elements are bound to each other, that will lead to differences in what we call bond polarity. And the reason for those differences is because the electrons are not being shared equally. So as the electrons are being shared, they're not shared equally, and this creates a difference in electronegativity. We call that a bond polarity. And this is caused by a difference in the electronegativity of an element. So, for example, we can have a spectrum of types of covalent bonds. We can have nonpolar covalent bonds where the difference in electronegativity, represented by the Greek letter chi, is 0. And that's when the two elements are exactly the same. Or we can have a very small difference in electronegativity between the elements, but not large enough for us to classify it as polar. We then have a range of electronegativity differences that we call polar covalent, and those can have anywhere between 0.4 to 1.8 difference in electronegativity values. And then above that, we have ionic compounds. And so we see that the distinction that we've made between covalent compounds and ionic compounds is actually kind of fuzzy, in the sense of in both cases there is movement of electrons, and the more electronegative element is pulling the electrons towards it, and if the difference in electronegativity is large enough, then instead of it being shared between those electrons, it gets pulled off and held by one of those elements. So these diagrams, these are using the maps of electrostatic potential. Also called MEPs. We've used that term already. And to be able to interpret them, I have this legend here for you. So areas that are red are areas of high electron density. That's where you've got lots of electron density in that area. Regions that are blue are low electron density. And then regions that are green are somewhere in the middle. And we can see another way of looking at this is that we can think of the blue areas having a positive charge and the negative areas having a negative, or the red areas having a negative charge, and then the green area somewhere in the middle is more neutral, and that ranges between having a partial positive and a partial negative charge. So in chapter 4, we looked at the periodic trends, and here in just a couple slides we're going to talk about the periodic trend for electronegativity. But before we do, let's first look at what the effect of electronegativity has on bonding. So this is a chemical reaction involving calcium oxide, which is an ionic solid, with water, and it forms calcium hydroxide. So we have an oxide forming a hydroxide, and we have a similar reaction with diphosphorus pentoxide reacting with water to form phosphoric acid. This is an oxide forming a hydroxide. Now, we have here, this is an ionic compound, and this is a covalent compound. And something to notice in terms of the structures of these is that they're very different from each other. The resulting compounds are very different. So by virtue of us having an ionic compound, the product is also an ionic compound. And there is an interaction between the calcium ions and the hydroxide ions. but each of those species retains its own charge. Whereas when we have our non-metal, our covalently bound compounds, those retain their covalent nature. And so the hydroxide that is present here in this case is a covalently bound hydroxide. And so it's still sharing the bonds, the electrons, but with the phosphorus. And so in both cases, we see that we can have hydroxides where we have the OH, that's the hydroxide group, but they can have ionic interactions or covalent interactions. And this is all due to the differences in electronegativity arising between the calcium and oxygen versus the phosphorus and oxygen. Now, how do we predict electronegativity? Again, we use the Greek letter chi, C-H-I, to represent electronegativity, and there is a trend in electronegativity. Let's first, though, define what electronegativity is. This is the measure of an atom to pull the electron density towards itself, but it must be in a molecule. So while we give each element its own value for electronegativity, we would not talk about the hydrogen atom having electronegativity. We can only talk about the hydrogen that's bound to some other element, be it carbon or fluorine or oxygen, etc. So we're looking at relative pulls of electron density towards itself. And the electronegativity of an element increases as we go up the periodic table, and it increases as we go to the right on the periodic table. Now, how can we think about this? Well, remember when we talked about the effective nuclear charge, and we said that effective nuclear charge increases as we go from left to right. Well, so because the effective nuclear charge is increasing, those elements are going to be able to pull more tightly on the electrons which they are sharing. Now, the rationale for the increase in electronegativity as we go up is different, but it's actually related to the shells. So remember, as those elements, the further up the periodic table we go, the smaller they get in terms of their overall size. Because they're smaller, the electrons are held more tightly, and therefore there's a greater attraction from the nucleus to the electrons which it's sharing. So elements with high electronegativity tend to accept the electron density. Elements with low electronegativity, we also refer to that as being electropositive, they will give up electron density. And so the differences in electronegativity is what will predict the bond polarity. If there's a high enough difference, then we consider those bonds to be polar. The range for the differences in electronegativity is between 0.4 and 1.8. Above 1.8, we call that an ionic bond, and below 0.4, we call that a nonpolar bond. So let's take a look at some examples. If we wanted to calculate the electronegativity difference between any two elements, we take the difference in their values. So for carbon, we have 2.55 and 2.55. The difference is 0. Look at, however, carbon to hydrogen, and the hydrogen has a value of 2.20, and so there's a difference of 0.35, so just barely outside the range of being polar. When you look at the nitrogen to hydrogen bond, there is a much larger difference in electronegativity, and so that bond is polar. And the way that we represent that is by using an arrow, and there will tend to be a cross sign here where it's on the positive side, and we use these symbols here. This is the Greek letter delta. This is a lowercase delta. So delta positive or delta negative is referring to the fact that we have a partial positive charge in this case, or a partial negative charge. As we continue on, we can look at even larger differences in electronegativity. And we've got here illustrating that the difference in electronegativity being larger is going to lead to a larger partial positive charge. And then finally, we have a full separation of charge, or an ionic bond, when the difference in electronegativities is above 1.8. So in later chapters, we're going to look at molecules and not just their bonds, but if you have polar bonds, then you have the possibility of having a polar molecule. And polarity is going to determine intermolecular forces. And this is going to be very important in a couple chapters as we're looking at chemical reactivity and the stability of molecules. All right, let's now do some practice. So, in which compound does chlorine carry the largest partial negative charge? Now, you're going to need to look up their values on the periodic table in order to do this, or at least that's one way you can do it. So why don't you look up the values on the periodic table and compute the difference in electronegativity to determine the partial negative charges. So pause the video, try that, and then come back. All right, welcome. So you should have determined from the periodic table the electronegativities for chlorine and fluorine, and seeing that fluorine is larger, it's going to have a partial negative charge. Chlorine has a partial positive charge. The electron density is pointing away from the chlorine to the fluorine. For B, the chlorine bond, because it's the same element, there's no difference, and therefore they're perfectly evenly shared between the electrons. For the chlorine-bromine bond, there's a difference in electronegativity of 0.2, and so there's a partial negative charge on the chlorine. And between iodine and chlorine, there's an even larger difference in electronegativity, about 0.5, which means that the partial negative charge on the chlorine here is going to be the largest of those four. All right, let's try one more practice problem. So rank the following bonds in order of increasing charge separation, or in other words, bond polarity. Pause the video, try this on your own, and then come back. Welcome back. So we want to rank them in terms of increasing bond polarity. So we put the least polar on the left and the most polar on the right. Now, you want to be able to do this by using trends in the periodic table, in addition to looking up the data if you need to. But most importantly is being able to do it based on the trends. So if we draw ourselves a generic periodic table over here, we know that electronegativity increases to the right and it increases as we go up. So if we place these elements in their relative locations, we have fluorine, carbon, oxygen, and then potassium. And so if we were to rank the elements in terms of electronegativity, then the potassium is the least electronegative, followed by carbon, then oxygen, then fluorine. All right, now we're not just looking at the electronegativities themselves, but the pairings. So fluorine to fluorine is going to have no difference in electronegativity because it's the same element. So it doesn't matter that the fluorine's the most electronegative element, because in this case, it's bound to itself. However, for the other cases, we're pairing the least electronegative with the most versus an intermediate with the most and an intermediate with an intermediate. So by looking at it that way, we could just kind of arbitrarily assign values if we wanted. We could say, all right, let's pretend this is 4, that's 1, that's 2, and that's 3. And then by looking at that, we can see that the least difference is going to be for the fluorine-fluorine. So we know that D and E cannot be the case. Our largest difference in electronegativity has to be between potassium and fluorine. So that rules out A. And then when we look at these two, we need to evaluate. And so in this case, we would have an intermediate value with the most electronegative versus two intermediate values. And so this is going to have a larger charge separation, and that gives us then an answer choice of C. Okay, that's it. Thanks for watching. Have a wonderful day.